In this video we're going to continue looking at gravity and specifically at gravitational fields. Before we get stuck into the gravitational fields, I want to just look at the idea of a field more generally. So the idea of a field is one that it's sort of a construct that's helped to make sense of some of the observations that we can see around us. It's basically just a region in which a force will act on an object, and depending on the properties of that object, it's going to depend on what the force is that's acting. And what I mean by that is that when we go through topic 2, we'll actually look at electric fields and magnetic fields, and they have certain properties that we need to be aware of. In the case of those two, it would be to do with electric charge and north poles, whereas what we're looking at here is to do with mass. So more generally speaking, we're going to see that a field is where a force would act on an object with a certain property if the object was placed in that region. So there's the more general idea about fields. If we look at the definition for a gravitational field, so this is one of those dot points, so something that you need to be able to basically explain pretty much word for word, but also have a good understanding of it. So a gravitational field is the region of space surrounding an object, and that region of space is going to be a region where another body or another object would experience gravitational forces. So in this case experiences a force of gravitational attraction. So there's the definition. What we can do with that though is unpack it a little bit more to make sense of the sort of the underlying meaning of that. So in other words, what we're really saying here is that gravitational field, it describes the force that would act, and not just the force but the magnitude and direction of the force. And if it's magnitude and direction, that means it's actually a vector, so this is a vector field. So magnitude and direction of force that would act on a mass, so that's the property that we're particularly concerned about with the object. It has to have mass. So if we're talking about say photons of light, they don't have mass, so we wouldn't talk about gravitational force acting on them. And so the particular thing about gravitational fields is that they're dealing with objects with mass. So there's an explanation that hopefully will clarify what that idea of a field actually is. It's about the force that's acting on a mass. Now, an easy way to visualize fields is to represent them graphically. So we'll have a look at that now. And basically, if you're representing a field graphically, you're going to use field lines. And there are a couple of things to note about field lines. And in order to consider what field lines look like, let's imagine that we're dealing with the Earth. So if we have this sphere or circle representing the Earth, so if we were to consider placing a mass, say somewhere at this point, it's going to experience a force that's going to pull it towards the center of the Earth, and so the field line that we'd see at that point would be directed down towards the Earth's surface that way. If we were to consider somewhere out to the side here, we'd see that the field line in that direction would be in towards the middle. Down at the bottom it would be up, and across from this side would be in as well. So we could continue to draw field lines in every direction there to show the fact that the field is directed towards the center of the Earth. So a couple of things to note there. The arrowheads represent the direction of the field, and that therefore means that they represent the direction of force at that particular point. So in each point you can see that the direction of those arrows is different, and so the field there, we'd call it a radial field because it's radiating out from the middle of the mass of the object, or from the center of mass. The second thing is the spacing of the arrows. So two quantities that we need to be aware of with field. First is direction, the second relates to the spacing. So the spacing of the lines shows how strong the field is. And we'll talk about what we mean by the strength of the field in a second, but just want to look at the fact here that when we've got field lines that are closer, that means that it's a stronger force or a stronger field in that region. So if you look at that diagram on the right hand side there, if we just sort of highlight a couple of regions, you can see sort of closer to the surface of the Earth, the field lines are more closely spaced. So in that region, we'd have a stronger field, so basically anywhere around the surface of the Earth. If we then look at further out, you can see that the spacing of the field lines out here is much further apart compared to what they were closer in, and so this the strength of the field in this region is going to be weaker, which makes sense. The further away from the Earth you get, the weaker gravity is, and so we can relate the spacing of the field lines to the strength of the field. If we now look more specifically at gravitational field strength, that's another property that you need to have a really good understanding of. The field strength itself is represented by the symbol G, so it looks like acceleration due to gravity, and we'll have a bit more of a look at that towards the end of this video. So that is the net force per unit mass. So we're basically saying, let's look at the force that would act on a mass divided by its mass to figure out how much force there is per kilogram at a particular point in the field. So we can consider that from the point of view of equations, and so we can define fairly easily then that the gravitational field strength G is simply going to be the force acting on a mass divided by the mass itself. So basically, if we've got a mass that we're sort of positioning here, we know that it has mass m. If we measure the force that's acting on it, we could then use those measurements of force and mass to figure out what the gravitational field strength is. So fairly straightforward calculation in that case. But we also know from Newton's law of gravitation the force that would act on that mass. So let's go back and note that again. So if we have this mass here, this would be the capital M that we're dealing with, and then we'd have to look at the distance between the centres of mass, being the distance r. So we know in that case that the force that's acting on that smaller mass is going to be given by gmm on r squared. So we can therefore rearrange that. We can get this expression of F over m out of that. So basically we divide both sides by little m, and we end up with G capital M on r squared. So this is the reason why we're using lowercase m and uppercase m. So that means that if we have this, if we sort of equate those two, we know that G is equal to F on m, and we know that F on m is actually equal to G capital M on r squared. So that equation's in the data booklet. So you can see there are two ways to figure out what the gravitational field strength is around an object. Either measure the force that's acting on a small mass, divide the force by the mass, and we get the gravitational field strength. Or if we know some properties about that object, so in this case the mass of the Earth, the radius of the Earth, we can figure out what the gravitational field strength is in that situation. So let's have a look at that. So if we consider on Earth's surface, we can actually calculate what the gravitational field strength is, and that's based on the values that we had from the previous video. So we'll use the expression here, G capital M on r squared, because we don't have any smaller masses that we're dealing with. So that's going to be the universal gravitational constant, 6.67 by 10 to the negative 11, multiplied by the mass of the Earth, which is 5.97 by 10 to the 24, and we're going to divide that by the radius of the Earth. So using the radius of the Earth because we're dealing with things that are positioned on the Earth's surface. So that's 6.37 by 10 to the 6 squared. That gives us a value of 9.81. And if you think about the units here, force divided by mass, that's newtons divided by kilos. So the gravitational field strength is newtons per kilo. Now, just to have a look at this in a slightly different way, if we think about Newton's second law, we again keep coming back to Newton's second law. We have F equals ma. And if we consider the units of force here, so I'll just put in brackets what the units are. Force is measured in newtons, mass is measured in kilograms, and acceleration is measured in meters per second squared. So really what we're dealing with when we're dealing with newtons, we're dealing with kilogram meters per second squared. So in that line above, what we can do is indicate that that's actually equal to 9.81 kilogram meters per second squared per kilo. So just making that substitution for newtons. You can see there that the kilos are going to cancel, so we're basically left with the quantity 9.81 meters per second squared. So the upshot of that is that we can identify that gravitational field strength is effectively the same thing as gravitational acceleration. The difference is the units of measurement. So in both cases we're dealing with the force due to gravity acting on an object. From one perspective we're worried about the strength of the field, and from another perspective we're worried about the acceleration that's acting on the object. So both interchangeable, so if you figure out the field strength then you've also figured out what the gravitational acceleration is. We'll have a look at a few more problems in class around that idea, so looking at things like satellites, what gravitational field strength they experience, and then perhaps looking at moons around other planets and those sorts of things as well.